And now, why can't trains go up hills? Now, the smarter ones amongst you will have recognised already, especially if you're a qualified railway engineer, this is a bit of a trick question because, of course, trains can go up hills. They're just not very good at it. Which, when you think about the topography of most of the world, is clearly a bit of a problem. Human beings can, admittedly rather sweatily, motivate themselves up a gradient of around 80 degrees, or 1 in 1 1/4. You do it every time you climb the stairs. Cars can manage gradients of up to about 30%, or 1 in 3, before their tyres start to lose grip, or their gearboxes explode into oily shards. But, as any 1950s schoolboy would tell you, the steepest mainline gradient in Britain is the fearsome Lickey Incline in Worcestershire. That is a gradient of just 2.65%, or 1 in 37.5 in the old money. And yet, that was considered so terrifying in the days of steam that a train would often have to be pushed from behind, or banked, to use the technical term, by up to 4 other locomotives. The problem is one of traction, or rather, tractive force, because for all their size and immense weight, trains really struggle to find grip. On a level piece of track, a train is a very efficient thing. The wheels are made of steel, and so are the rails. If you rub 2 pieces of steel together, you will find they produce very little friction, much less than you'd get between, say, a tyre and a road, or even much less than you'd get between your finger and a piece of glass. Train wheels are also very narrow and profiled in such a way that only a tiny part of them rests on the track. If you take a typical 12-wheeled locomotive with a weight of 120 tons, then the size of the contact area between all those wheels and the track is about the same as 2 50-pence pieces, which for people watching in countries outside Britain is 2 coins roughly so big. Which explains why trains are so good at slicing the hands and feet off distressed damsels who have been tied to the railway line by Edwardian ruffians. It also explains why trains are able to move at all. The entire weight of the train presses the wheels down into the rails and creates grip, even though it's steel on slippery steel. The tractive force has to overcome the weight of the train, friction, and, as it starts to go faster, aerodynamic drag. There comes a point where the aerodynamic drag has built to a point where it's equal to the tractive force, and at that point, the train has reached its maximum speed. Because weight is so important to the generation of tractive effort, it is possible that a fatter, less powerful locomotive can generate more of it than a lighter but much brawnier one. The upshot of this is that on a nice, straight, level, flat piece of track, a train can reach a surprisingly high top speed despite a limited power output. The Eurostar only generates something like 22 brake horsepower per tonne, or less than a small city car with 5 fat blokes and a month's supply of pies on board. And yet, the Eurostar can do 200 miles an hour. The car will struggle to crack 70, partly because of the inefficiency and the drag created by its big rubber tyres. But on hills, which the car will crest gracefully, probably in second gear, then the train will run into problems because the gradient will add to the drag created by its weight, but the tractive force remains the same. If it's a powerful locomotive, it might well start spinning its wheels. If it's a puny one, it will probably just grind to a halt, and then the guard will come on the tannoy and blame the stoppage on operational difficulties or something like that. But the net result is the same. You miss your dinner. But for trains, hills cause an even bigger problem, which is how to get down them, because then all the braking force is concentrated in that same tiny area where the wheels meet the rails. And if it's a particularly steep incline or a particularly heavy train, or even if the rails are very slippery, then your train can run away. So you know those excuses we've all mocked over the years: mud on the line, leaves on the line, the wrong kind of snow. It's all true, actually.
I'm Rob Bell. In this live experiment, we're asking the question, how do trains go around bends? Now, last time we were on a train, you might have heard the train screech, make a really loud screeching sound when it's going around a corner sometimes. Don't worry, it's all normal. It can be quite annoying if you're trying to listen to your music or read your book, but it's there for a very good reason. Train wheels are different to the wheels you find on, say, cars or bikes, and they're different because they've got a ridge running all the way around the outside. That ridge is called a flange, and it's there to help prevent the train from sliding off the track. But that screeching noise is what you get when that flange rubs up against the side of the rail. You've got a metal on metal contact, and it makes a loud noise. But train wheels are different in another way as well, and that's what this experiment is all about. For this, you're going to need some large plastic cups, 4 of those, an empty bottle, some scissors, some old hosing that you might just have, some gaffer tape, normal wheels that you might think of as a car, kind of uniform disc shape like this gaffer tape, and it just happily roll along. Train wheels are different. They're a kind of truncated cone shape, slightly tapered, so that you've got a larger circumference at one end than you do on the other end. And it's this little detail that's a piece of engineering genius that allows trains to go around corner. And this demo is going to show us why and how. To get started, we need to put down some rails. For our rails, we're using our garden hose. We're going to stick these down to the table using some gaffer tape. Then we're going to start to bend it ever so slightly. Well, you want to make sure that it's about 1.5 cups lengths away from the other one. So about there. That should work. So start it off going straight again at the end of the bend. Right, we've laid our track down. Now we need to make our model train wheels. Now, this is where the demonstration all comes in, because we're going to have 3 sets of wheels with different designs that we're going to trial out on our tracks to see which ones go around the corners best. Our first model is ready to go. It's our empty plastic bottle, and it's got straight edges. We're then going to use our plastic cups, and we're going to do 2 different designs with these. We're going to tape 2 plastic cups together so that the big ends are in the middle. And for our third design, we're going to do exactly the same, but we're going to tape the smaller ends together in the middle, like that. There are our 3 model sets of train wheels that we're going to send down our tracks to see which one stays on the rails better as it goes around the corner. First up, the flat wheels. Let's see what happens when that goes down. Not much, it pretty much goes straight on. Let's try these with the small ends in the middle. Okay, off it goes. Oh, well, that's completely rubbish. It came off halfway down and started turning the wrong direction. Okay, finally, our model with the big ends taped together in the middle. Let's see what happens. Oh, no, that's much better. That pretty much stayed on till the very, very end when the curve got quite severe. So it was this model here that worked best. The fact they're on a fixed axle means that the 2 wheels are fixed onto the axle in the middle, so that if one turns, the other has to turn at exactly the same speed. And that's great for when you're going in a straight line. Down it goes. But if we want to go round a bend, because the outer side of the bend is longer than the inner side, you need this wheel on the outer side to turn faster, but it can't do that because they're on a fixed axle. So the other way to get wheels on a fixed axle going round a bend is to have that wheel there bigger than the inner one. Now, this time we've got a much bigger, a stupidly bigger wheel on the outside than we do on the inside. And if we let go of that, it will only turn. It just wants to turn. No surprises, really. You'd expect that. So hang on. Let's get this straight. On a train, when you're going straight, you need wheels of the same size, going round at the same speed. But when you come to a bend in the track, you need a bigger wheel on the outer edge of the bend than you do on the inside. I've never seen anybody go out and change wheels halfway through a train journey. That's not what happens. It's the fact that the wheels are actually tapered that allows trains to go around corners. Now, let's go back and have a look at what actually happened with our most successful model as it went down the track. So it started going straight with our axle here and our wheels in the middle, so that you've got the same circumference of our cups here going down the straight bit. And unsurprisingly, it goes straight on. Perfect. Comes to the bend, our wheels on this side, or what's the part of the cup that's in contact with the rail, is a much smaller circumference, And on this side, as it rolls down, the part of the cup that's in contact with the track gets bigger because of the fact that they're a truncated cone. And that is the small piece of engineering genius that allows trains to go around.
I'm driving at 50 miles an hour, and if I need to make an emergency stop, the highway code dictates that I need a total distance of 53 metres. That's 38 metres of braking distance and 15 metres of thinking distance.
And if traffic builds up and I slow down, my stopping distance obviously falls. The faster I'm going, the larger the space in front needs to be. And if I slow down, that space gets smaller. We could increase capacity on the railways by getting trains to follow these principles too.
It's essentially like turning a fixed block system into a moving block, and that's going to make all the difference.
So how would you make it work? Well, you'd need to know everything about the train in front, how fast it was moving and its position.
And if you knew your speed and your position, you could then calculate how close you could travel behind the first train safely. Simple, in theory.
And it's exactly what they do here at the Docklands Light Railway in East London. Each train's exact position is worked out using wires laid out along the track. These wires transmit signals to and from the trains.
The loops of cable cross over every 25 metres along the track, and here's one of those points. Now the train counts the amount of times it travels over one of these cross points, and that's the crucial part of the system.
The train can count these cross points because the electrical signal changes direction at each twist.
This is the train's onboard computer system, the nerve centre of the train. And let me show you what happens when the train passes over one of these crossover points. The current is running in one direction as the train approaches the crossover. At the crossover, it flips 180 degrees, what's called a phase change.
This oscilloscope measures the direction of the signal below, and you can see how it flips as the loop passes underneath the train.
And it's this that the train registers and counts every time it passes over a crossover.
Each pulse identifies the train's position within the 25-metre loop. Then a second system measures how many times each train wheel rotates. Between these two systems, the train position can be tracked down to just a few centimetres.
The exact speed and position of each train is relayed back to this control centre, and the computer system here then calculates how close to each other the trains can travel safely. That information is then relayed back to the trains so they can move accordingly.
Using moving block, the DLR system is able to run more trains closer together than a conventional fixed block system, which means the line capacity can be far greater. And it's flexible enough to be able to deal with almost any unexpected occurrence with ease.
The police just delayed the train at platform 2. You got any idea why that was, huh?
And the system is so safe, it's not only done away with all signals, but there's also no need for onboard drivers.
Thanks to all of this technology, moving block is going to revolutionise the way our railways will be run in the future, dramatically increasing rail capacity and efficiency.
Well, firstly, there's a technical reason why trains are great. They're very big and they're very heavy. They take a very long time to accelerate and a very long time to stop. The physics involved is quite sort of awesome. It's a lot of mass and therefore a lot of energy. A big, long train can weigh, 1,200 tons. That's a lot of stuff. I think the other thing that's appealing about trains, the thing that makes them romantic, is a slightly more philosophical one. It's because if you go in a car or on a motorcycle or on a bicycle, obviously, generally, you've got to stick to the roads, but you have a choice. You set off and you decide where you're going to go. When you get on a train, you submit to it because it has already been ordained where that train will go, even if you don't know where it's going, even if you're on a mystery excursion, and you have to give in to it. And there's something exciting about that. There's something almost sort of pioneering because it's slightly unknown. And the view from a car or from inside the helmet of your motorcycle is of things that are about to happen, things that are coming towards you. But on a train, you sit and you look out of the window at the side, and your view is of things that have just passed, just occurred. So you're sort of looking at the past in a way as you go along. The very recent past, but the past nevertheless. It's as if the scene has been formed by the train and is pushed past it like the wake of a boat, and it's something that wasn't there before. I think it's fascinating. I like trains a lot. I like watching trains. I know you shouldn't admit to that sort of thing because everybody goes, Sado, train spotter. I don't mean I go and collect the numbers off them, you know, looking down over a bridge. It's just that when you see a train, it is exciting, isn't it?
Is there anything that annoys you about a train journey?
The thing that annoys me most about train journeys is that they don't actually go from and to where you live or where you want to be. I think that's the big disadvantage with them. That's why things like cars have triumphed. And the great irony is that people talk about intercity railways reducing congestion, taking goods off the road and so on, and that's all a very nice argument, but the real problem, the place where the congestion exists, is the bit between where you live and the station, or between the goods yard and the supermarket that needs to be supplied. So the train doesn't actually answer that unless you have railways running through the towns and cities. But in order to meet the sort of demand that's placed on cars, this railway network would have to be so complicated there'd be a station at everybody's house and there would be rails down every single road, and that clearly can't happen. It's too complicated. But I think, you know, trains, even in Britain, everybody goes, oh, the railways are so backward and underfunded and underdeveloped in Britain. And, well, maybe they are compared with bits of Switzerland and France, but they're still fast. I went on a train from London to York, and it took about an hour and 35 minutes. It went like the clappers. It was at least twice as fast as the car. Cars, in reality, are actually pretty slow. They're just convenient. That is the truth. I know I shouldn't say that. I work on a car program. Cars are great fun. They're an interesting hobby, they're stimulating, they're exciting, but they're not a quick way of getting anywhere. You can't actually feel it, obviously, but you sense the enormous mass of a train. So I had a go at driving a steam locomotive that was pulling a big 12-coach train. And you have to, for those reasons we've just been talking about, the traction and so on, you have to get it going very, very gingerly. You sort of squeeze the regulator and close it again and watch the pressure in the cylinders build and drop. And it actually creaks at first. It just goes... You know, you just about sense that it's moving, and then it's just got enough grip, and it goes, and it moves, and you think, that's fantastic, it's moving. And it gets to about 2 miles an hour, and then you feel that it's running away. It's a strange sensation. You suddenly panic, and now what? And it really, honestly, it is going this fast.